Okay, chemists, today we're going to look at a very well-known reaction called the aldol reaction. It's a cross between the words aldehyde and alcohol. It's not a person's name, it's just a hybrid of the functional groups. And you'll see why they call it that shortly. It's a reaction of carbonyl compounds in hydroxide and in base to make alpha-beta unsaturated carbonyls. We'll show today how we do it with ketones and aldehydes, but we'll see there's some very similar reactions that involve other carbonyl-containing compounds. And you might be wondering why there's a cartoon of an ostrich on your notes. We'll get back to that later. It's a shortcut trick that some of my former students actually came up with for how to figure out the products of these kinds of things. So let's pan over to what the aldol reaction looks like. We'll look today at how it involves a ketone reacting with an aldehyde. And in the presence of hydroxide, which means negative charges, you can make what's called a beta hydroxy ketone. And you can see where that name comes from. Here's the ketone. If we look at the alpha carbon, remember where you make an enolate, one away from that would be the beta carbon, so beta hydroxy. We'll also see that if you actually subject these beta hydroxy ketones to the same basic conditions but just thermally heat it up, that's how you actually get the unsaturated ketone. That's how you can get an alpha beta unsaturated ketone, which you might remember we can also call an enone. And these are useful because we used them with things like conjugate addition reactions involving cuprates, where the cuprate could attack the beta carbon and you would get a substitute ketone. So now we finally know how to make these things. Let's figure it out. Let's learn how it happens. All right, let's draw the mechanism for how this works. Let's start with the ketone. And in the presence of base, ketone is going to lose a hydrogen from the alpha position, and you get an enolate. And that enolate is a nucleophile. This is an enolate. That's what we learned about in the previous lesson. These are nucleophilic. And we saw yesterday, or I should say in the previous lesson, that they can do things like SN2 substitutions, where they attack alkyl halides and have a halide leave. Well, today we're going to see they can react with other electrophilic things like aldehydes. And we've seen aldehydes act as electrophiles before. They get attacked at the carbonyl carbon, the pi bond goes up. That's exactly what happens here. So draw an arrow from that enolate carbon to the carbonyl carbon of the aldehyde and send that pi bond up to the oxygen, and what you get is a new carbon-carbon bond and an oxygen anion. So we form the beginnings of an alpha-beta substituted or eventually unsaturated carbonyl compound, and this is how we get to the hydroxy ketone. If you go a step back, we made water a moment ago. I'm going to use that water molecule right here and show that anion taking the H. We are under basic conditions, so you see negative charges in your intermediates, and that's how you get your beta hydroxy ketone. This we call the addition product, just because the two molecules add to each other. But as we saw in our introductory part, there's another possible product that happens from just heating this up under the same conditions. And we're going to start with using the hydroxide ion, which we just made. It actually forms another enolate. I'm going to draw out the enolizable hydrogens here on the alpha position. So hydroxide can take one of those H's away. You form another enolate. It's all about the enolate in this unit. You might wonder, why doesn't this just deprotonate that hydroxide? Well, it does. That actually gets you back to where we were, which is really an indication that almost all of these steps are highly reversible. The aldol mechanism has a lot of reversibility to it, but it's going to funnel into a very substituted product here. This is an enolate, and just for fun, I'll remind everyone, enolates are fairly stable because of a resonance contributor. Remember that negative charge can delocalize up into the pi bond. That's why we can get the negative charge on the carbon. It's really rare to see a carbanion like this, but because it's alpha to that carbonyl, you can have that happen. So how does this turn into the unsaturated ketone, which we drew up above? Well, that enolate actually kicks out the hydroxide to bring that negative charge back down to form a pi bond, take that other pi bond and make a carbon-carbon double bond between the alpha and beta position, and you kick out hydroxide. We are in base, so we can actually kick out the hydroxide, and it's the enolate that does this. The enolate kicks out the hydroxide. That's why this happens, and that's how you get your what's called condensation product. So we had an addition product over here, the beta hydroxyketone, and the condensation product, which is the alpha beta unsaturated ketone. So why did we draw this ostrich thing earlier, or why is it already there, actually? Well, some of my students from the past said, you know what, we can come up with a shortcut to figure out how these reactions work. If we imagine an ostrich, I'm going to very poorly sketch an ostrich, which is a bird with long, skinny legs, one of the fastest birds out there. And it's an apocryphal myth that ostriches bury their head in the ground. There he is, burying their head in the ground. But really, I think it's just that they bend down to eat food off the ground. So if we imagine that our ostrich is an aldehyde, that's a little too thick of a font, let's change that. And the ground is our ketone, the product sort of looks like the ostrich stuck its head in the alpha carbon of the ketone. Just turn this ketone upside down and form a bond right there between the carbon-carbon bond, and that's how you get your alpha beta carbon. You don't have to like that rule, but it's a trick some of my former students more or less invented, and they even called it the ostrich rule. So I pass it on to you. Anyway, let's use our organic common sense and see if we can figure out how to synthesize the following aldol addition products using what we just learned. So these are all products of a hypothetical aldol reaction, and I'll point out, doing the first two, and then I'll have you try. Look for the carbonyl that's still there, and find the alpha and beta positions. There's the alpha position, and there's the beta position. When you go backwards, you have to think about making that alpha-beta bond, except the starting material, the alpha carbon, well, the alpha carbon you simply fill in with H's, and the beta carbon, make it a carbonyl. Make it a COW. CO double bond. So let's draw that. Let's go backwards, and I'm going to redraw this exactly the same, but I'm going to break that alpha beta bond. So if I do that, the part on the right would have this. The part on the left would have that. I do not have that bond anymore between the two. My notes say the alpha position, fill in with H's, right there, done, filled in with H's. The beta position, make it a carbonyl. Okay, so I don't want an OH here, I want a CO double. There we go. So if I react those two things with hydroxide and water, I should cleanly get my beta-hydroxy, in this case aldehyde. And if you look, you'll notice these are actually the same molecule. This is a self-aldol. Sometimes you call it an aldol selfie, because these are just two equivalents of the same thing. That's butyraldehyde reacting with each other. This works if you want to make a condensation product as well. There's an alpha-beta position, and we want to think about making that bond. So let's do the same thing. Let's go backwards. I'm going to imagine breaking that alpha-beta bond. The right half would look like all the carbons are still there. There's a ketone in this case. There is a benzene ring. And the alpha position, I'm just filling in with H's. Done. The beta position, I draw in all the carbons. My beta carbon is right there, so I have to make it a carbonyl, which in this case is a ketone. And if you look, this is also a self-aldol, just by coincidence. This one, if I fill in the reagents, I'm going to put hydroxide, but also heat. It's that heat that drives the condensation product. Okay, I want you to try the other two. Hit pause and see if you can figure out what the starting materials would be for C and D. These are intramolecular aldol products, but do the same thing. Find the alpha-beta bond, break it, and follow your notes up above to figure out what the starting materials look like. Okay, let's see how you did. So I'll find the alpha-beta bond. That's alpha and beta right there. I'm going to make the alpha-beta bond right there. And then if I go backwards, I draw everything in terms of the carbons. I just don't draw that alpha-beta bond. The alpha position I fill in with H's. The beta position I make it a carbonyl. So let me get rid of that OH and make it a carbonyl. This is not really a self-aldol, but it kind of is. It's just intramolecular. This is the addition product. It's got the alcohol still there. So this is hydroxide and water, but no heat. Look out for that heat. That's what drives the condensation product. That's got to be true for this last one. This is base, water, and heat. There's other reagents that do this. I'm just using aqueous hydroxide as an example of a good base. Anyway, here's the alpha-beta bond. So I'll draw a dotted line through it to break it, going backwards. And my starting material will have all the carbons. The alpha position, I fill it up with H's. The beta position, I make it a carbonyl. So this is just a long linear diketone. It's not even cyclic. Okay, so that's a short introduction into how the aldol works. I said earlier that this is actually a reversible reaction, and here's an example that shows one key feature of the aldol reaction, which is a preference for making stable rings. Specifically, 5 or 6-membered rings are much more stable than, let's say, a 7-membered ring like we're starting with over here. So much so that if you started with something that looks like an aldol product, it can actually turn into a different aldol product, and it's thermodynamically going to stay as that. So let's see how that happens by writing out the mechanism for this forward aldol that follows a retro aldol, a backwards aldol. Okay, so let's start. The first thing that happens in a retro aldol is going to be whatever the last step was in the forward aldol. So go back up to the mechanism. The last thing that happened in the forward aldol was hydroxide leaves. That means in a retro aldol, the first step is hydroxide comes in, and it will form a bond with the beta carbon. In fact, it looks just like a conjugate addition of hydroxide to this unsaturated ketone. So we get a 7-membered ring. I have my ethyl attached. I have a new OH, and now I have a negative charge on that alpha position. Thinking back to the mechanism up above, next we're going to get to the beta hydroxy ketone, the addition product, or I should say what looks like the addition product. And you do that just by protonating that intermediate. you get to there. Now if I keep looking back up above, you can do that too. Prior to this addition product, so the next step is going to be to get an anion on this carbon. We just used hydroxide, although we just remade hydroxide. So we're actually toggling back and forth between hydroxide, water, and now I've got hydroxide. That's a good tip when you're doing these mechanisms. If you're sort of toggling back and forth between hydroxide and water as you're doing these mechanisms, you're probably on the right track. It's kind of like back in the acid-catalyzed mechanisms when we would go back and forth between H plus and water. Now we're going back and forth between hydroxide and water, being under basic conditions. So what can hydroxide do? Hydroxide can deprotonate that H on the alcohol, and you get an oxygen anion. We're still doing the retro aldol, and here's the trickiest part, I think, of envisioning the retro. Remember that the aldol forms an alpha-beta bond right there, alpha to the ketone in this case, and then the beta position now has an alkoxide on it. So in a retro aldol, that bond has to break. Well, that happens from the oxygen bringing a pair of electrons down, and you break that alpha-beta bond, and you take that pair of electrons, and you could just put it right on the alpha position. This is all still a retro aldol. And now you have an open ring, 7-membered plus 2 more with that ethyl group, which I'm just going to redraw as a long 9-carbon chain. 2, 4, 6, 8, 9. With 2 ketones and a negative charge all the way out here on the end. So what happens next is we get back to the actual, what looks like aldol starting material. I'm going to use a water molecule to just protonate that enolate. And I get my 9-carbon diketone, 2, 4, 6, 8, 9, with 2 ketones. And that's the entire retro aldol. That's just the aldol in reverse. We started with what looks like a condensation product. We turned it back into 2 carbonyls intramolecularly. But we're going to keep going. This is not done. This is now going to go in some kind of forward sense and make this product, which is a 5-membered ring. And this is a good time to just zoom in and really look closely at anything that you think could ever do an aldol. Every time you have an aldol starting material, it's worth looking at every possible enolate you could form. What's an enolate? It's just the anion alpha to a carbonyl. We just saw one, alpha to that ketone. And if it cyclizes by forming a bond with the other carbonyl, that would give us a 7-membered ring, which we know is not favorable. Oh, whoops, did I lose my carbon count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I think I gained a carbon. Let's back up for just a second. We gained a carbon here, didn't we? Easily fixed. Easily fixed. There we go. That means this was 1 carbon too many. See, even your teacher can get the carbon count wrong. But he checks. Checks and fixes it. So, we just saw that we could have had an enolate here, and it could react with the other carbonyl in an aldol. That would give us a 1, 2, 3, 4, 5, 6, 7-membered ring. Not only is that a less stable ring size, it just gets us back to where we started. That's going all the way back to the starting material. So what are some other possible enolates? In addition to this one, we could have one all the way out here, alpha to the other ketone. Well, that would give us a 1, 2, 3, 4, 5, 6, 7-membered ring as well. So that's not likely going to happen. There's 2 other possible enolates. There's this one, which, if we imagine it cyclizing with that carbon, would give us a 5-membered ring. That sounds good. However, there's also this one, which, if it cyclizes with the other ketone, gives us also a 1, 2, 3, 4, 5-membered ring. Now, that means there's 2 possible enolates, and frankly, both of them likely form. But we're trying to explain this specific product. So looking at that product, I want you to just hit pause real quickly and see if you can figure out which enolate actually forms to get that product over here. Okay, well, welcome back, and we're just going to finish up here. Remember, the forward aldol that we're about to do, to get to that, makes that alpha-beta bond. And I can see here an ethyl ketone still intact. So this ethyl ketone is still intact, which means that is the part that forms the enolate, and the methyl ketone on the other side will end up getting attacked. So, hydroxide will take away one of those two hydrogens. We know this because we figured it out by looking at the product. There's my new enolate. And then this will form a bond with that other carbonyl carbon and send those electrons up to the oxygen. And I'm going to draw this ugly first, just so I don't lose carbons, because I have a habit of doing that. So I recommend you do the same, unless you feel really good about how you're drawing your drawings. There's a new bond between that alpha carbon and that used to be the ketone. There's a new bond right there, so I'm just going to draw it like so. And now I will redraw it. This is a 5-membered ring. 1, 2, 3, 4, and 5. So I'll draw a 5-membered ring. And I'll arbitrarily pick the carbon at the top to be carbon number 1. Carbon 1 has an oxygen anion on it, and it has another methyl on it, and it's also attached to carbon 2, which is attached to 3, 4, and then 5. 5 happens to have a ethyl ketone attached to it. So there's the rest. And now I can more easily see how this intermediate is going to become this. We have to protonate that alkoxides to make an OH, make a new enolate next door, and then unsaturate it. So let's do that. So we just used hydroxide. Let's use water simply to protonate. Here comes the aldol addition product. And how do we get to the condensation product? We're going to lose that alpha hydrogen to make another enolate. And you do actually make it as an intermediate. Negative charge right on that alpha position. And the very last step is for that enolate to kick out the hydroxide. That'll give me a new carbon-carbon bond right there, which is that, an ethyl ketone and a methyl on that carbon-carbon double bond. So that's a very lengthy mechanism because it involves a forward aldol, which follows a backwards aldol, what they call a retro aldol. I'll just wrap up by highlighting some features of the aldol reaction. We just talked about how it's reversible. The condensation product is always favored if you have a thermal condition. However, if there are ketone-ketone reactants, you can't ever get an aldol addition product. It actually just reverts back. So these hypothetical aldol addition products that are beta-hydroxyketones, you can't ever stop at those. They're not thermodynamically stable compared to a diketone or an alpha-beta unsaturated ketone. However, you can get addition products as long as you have at least one aldehyde. We'll see more examples of what we mean by that, but that just gives you a heads up as you start to look at the homework problems on the back. Okay, that's a good introduction to the aldol reaction.